Why do we bother learning the limit? Here's the thing, there are two things that we have to discuss with the definition of limit: continuity as well as the differentiability. So if I look at the continuity here, it says both the limit and then the value. So we talked about the continuity using the 5x squared plus x over x, right? The limit value might be defined, function value might be defined, but if they are not the same, then we say it is not continuous, right? So if you look at this, we have a limit value here, the function value, both are defined, and they must be the same to claim that we have a continuity at a certain point. So if you want to talk about the continuity at a certain point, three things in fact: find the limit, define the function value, and see if they're the same. Okay, so make sure for continuity we need to define what the limit, function, hence they become the same thing. Okay, and for those, let's have a look at some of the examples of the continuity as well as the discontinuity. Okay, so what I'm going to show you is the following. Hold on a sec, let me just go to the limit definition here. The page number 86. 86 is going to be what it is. So I understand because of the contrast with the white background might not be so visible at the moment, but it's okay because I can zoom it in and it will look visible then. Okay, hold on a sec, let me change into the blackboard here. Alright, so I'm going to show you the examples of a continuous function as well as the discontinuous function, and for those we have different names of it. So let's have a look at this. For him it's a quadratic function, x squared minus 3, and for me, I am able to sketch this without taking my pen away. You see, I'm able to sketch this without taking my pen away. That I call it continuous. This is going to be continuous. Okay, so if you can sketch the function without taking pen away, then voila, we call that as continuous function. Alright, so now if you look at the second example, I have a rational function, right? For the rational function, I am able to sketch certain part, but I have to take my pen off and then sketch the other part along with the vertical asymptote. And that, we call it infinite discontinuity. We call it infinite discontinuity. So anything to associate with the discontinuity with the vertical asymptote, we call it infinite discontinuity. And then you can already see that these sine functions, since I'm able to sketch this without taking my pen away, will be something of continuous. Okay, but let us have a look at the fourth one. Let us have a look at the fourth one. If I look at this function, right, it's a piecewise function. It's a piecewise. It was a linear up to certain point, jump, and then another linear, right? But this gap, because of this gap, I need to, make sure I take my pen off and go to the second one. And for this type of jump, this type of quick jump, we call it jump discontinuity. This will be defined as jump discontinuity. And then the way we can show that it is not continuous by the definition of limit is going to see the left limit. Left limit coming from the left is going to be given by 1. But the right limit at 1 is going to be 2. So since the limit doesn't exist, I know it will be discontinuous, because continuity, three things were required. Limit exists, function value exists, and they are the same. However, since the left and right limit are not the same, hence the limit doesn't exist, so we call that as the discontinuity. That's jump discontinuity. So, if you look at this famous floor function, which covers just the integers, will be also consider, jump discontinuity. See, at integer values, they are jumping, so it's going to be jump discontinuity as well. But let us have a look at the last example. This is the more interesting example. If you look at the last one, you see, for him, what it said is that I defined it quadratic. You know, I'll write it for you. I think it's not too visible here. It says x squared, x not equal to 0. You see, this is a quadratic function. Everything except 0. But at 0, what the function defined was for 2. At 0, they arbitrarily put 2 here, you see? So in order to sketch this function, what I'm going to do is I'm going to sketch like that, but take my pen off, put that point, and then draw the remaining function. As you can see, I took off my pen in order to sketch this function, hence I can know that this is going to be discontinuous. However, and it's a lot more lenient, more generous than the other one, right? Because if I could just get rid of this point and make it into the origin, that function will be just nice quadratic polynomial continuous function. Hence, we call this as a removable discontinuity. We call this as a removable discontinuity. In a way that I can get rid of that point to be the origin, then I can make this as a continuous. Okay, so we have seen the 3 different discontinuity: infinite discontinuity, jump discontinuity, and removable discontinuity. All right, so then I'm going to go to the slide here. Here's the thing. Proving continuity or discontinuity is going to be your main job with the limit definition. But from this point, it's going to get slightly hard. It's going to get slightly harder. So please fasten your seatbelt and see what we can do. I'll show you one first example, and I want to show the continuity at x equal to 1 for this piecewise function. There are a lot of piecewise functions that you are going to be equipped, and then you need to mention about his continuity and differentiability. But for this piecewise function for proving continuous is pretty simple. What you need to do is to have a look at the left limit and right limit, right? Left limit being coming from the left hand side, so I'm pretty sure this is going to be the left limit, right? And then the right limit, right? So if I plug those values in, right, x equal to 1, that's just 3 minus 1, that's 2. If you put 1 in here, 1 plus 1, that's 2 as well. So the left and right limit exist, and they happen to be 2. So what's the second thing that I have to define? The value of the function. So if I put 1 into the function, then as you can see, it's a closed interval, so I'm pretty sure I'm going to define my function value onto the second piece, and it becomes 2. So the limit exists, function value exists, and they are actually the same. So we can say that this is a continuous at x equal to 1. Easy peasy, lemon squeezy. But what is going to be slightly harder? Proving discontinuity is going to be slightly harder. If you look at the sine 1 over x, if you actually put this in a graphing calculator, it gets crazy. It's a crazy oscillation. But what we want to show is that it is not continuous. I want to show that it's discontinuity at x equal to 0. Whenever you have to show discontinuity, what is a very popular technique is to use the sequential limit of the function. So we're going to revisit that definition, the one that we defined yesterday. But also I'm going to also talk about this piecewise function to prove the discontinuity at x equal to a. So that is how we do this. This was the sequential limit definition. If the sequence converges, okay, and then the function is continuous, 2 conditions, then even if you composite the sequence onto the function, the limit is preserved. That's what the sequential limit definition was, okay? But what we want to talk about is the contrapositive. What if the sequence limit converges, but you composited it on a function, but didn't get the same limit? That means function is not continuous. If it had been the continuous function, then the limit would have been preserved. But if you could show that compositing the sequence onto a function and shows that their limit is not preserved, then we can say that the limit of the sequence at a, the function will be discontinuous. Okay, so that's what we are doing. So this concept is not easy, right? Because it's for the very first time we have seen it, right? So let's take our time slowly and see what we can do. So this is the aim that we wanted to prove. We wanted to show the discontinuity at x equal to 0 for this function. So step number 1, what we need to do is to, we can use a lot of a definition of continuity, but what we're going to use is the sequential continuity. We're going to use sequential continuity on him.